So, hey everybody, let's do the second part of the generating functions lecture. I have a nice board here. And let's just recall that generating functions relate sequences. So in this example, a sequence starting at A1, A2, A3 with functions. And in this case, the function g of x being equal to, and then from n is equal to 1 to infinity of a n times x to the power n. And the trick was that we want to know something about the sequence, and we can get there by doing the right manipulations to the functions. And I want to give you an example where you have a sequence where which is defined recursively. So the first statement is that A1 is 0. And the second statement is that an plus 1 is given as, and now I have to get my script, that's the same script as on the website. It's 8 times an plus 9 times 10 to the power n minus 1, as long as n is larger than 1. So otherwise you get this expression. So let's check if we have a1 equal to 0. Then we can also compute a2, which would be 8 times 0, 8 times a1, and then 9 times 10 to the, and you have to check if you have a 2 here, you get 1 minus 1, 0 in the exponent, and this evaluates to 9. And the same way you can compute A3, etc. But what you're actually interested in is the question, what's my sequence? What is a formula for an? You might think of the example where you're computing the amount of floating point calculations you need for a certain algorithm, and you can only express it as a recursion, the amount of floating point algorithms for an array of size n plus 1 depends on the amount of floating point operations it takes on an array of size n. Maybe you have a divide by conquer algorithm. In any way you're interested in a formula for the an. And the way to go there is getting the perspective of generating functions. Yeah. So how do you get a g here? You start just writing an plus 1, and if you look at our function g, then an plus 1 we would have to multiply with x plus n, x to the power n plus 1. We can multiply the left-hand side of this equation with this, but then we also have to multiply the right-hand side of the equation. So we are putting in an x n plus 1 plus 9 times 10 to the n minus 1 x to the n plus 1. And this equation is still valid for n larger than 1. So if we want our generating function, we can sum over everything on the left-hand side, but then we also have to sum over everything on the right-hand side. And now you recognize, so the sum goes from n is equal to 1 up to infinity, and then on the right-hand side as well. Okay, nice. That's a bit awkward that we have n plus 1s here and our sum starts at 1. Let's fix this By starting the sum at 2, we're starting one step later and we have to correct. And we get a sum over an times x to the power n. So if you're doing these manipulations, it's always good to just check with which term does the sum start. So now n is equal to 2 and it starts at 2. And before it was also starting at 2. So that's a consistency you can check. And if we want to have our g, then we can replace the n is equal to 2, the starting point of the sum, by 1. But then we get one element more. So for the equation to still hold, we have to add that element which we add into the sum, and that was a1 times x to the power 1. Luckily, the a1 is 0. So this thing we have to add is in fact 0, and nothing truly happens. Okay. Here is our g. And actually it's also here, but you have to squeeze a bit. So the way we see that the g is in there is by rewriting and pulling the 8 out and pulling an x out. Then of that sum, we still have left n goes to 1 up to infinity of an x to the n. And now it's only x to the n because I have taken one x out. And for solving this exercise, it works nicely to take 9 and x to the power 2 out, because then what we get in the equation has 10 to the power n minus 1 and x to the power n minus 1. So 10 to the power n minus 1, x to the power n minus 1. And that is something we can rewrite as (10) times x to the power n minus 1. And the sum was still running from n is equal to 1 up to infinity. So that's nice. This is 0, so I can remove it. And this is not needed at the moment. So this sum is called in the script, they just use a capital S. And you can see that you have an S here. And you have an 8xs. So we have an equation for s, and if we want to know our generating function g, or the s, then we just have to solve this equation for it. Or maybe just as a bit. It's still some steps going ahead, but the first thing we can do is we write an equation for s. So we get s minus 8xs. I'm just bringing all the s on the same side of the equation. And this will be equal to 9x squared sum over 10 to the power x n minus 1. So the trick is, as I told you, to go via the detour of a function. And we still have a sum written here, but we can write down a nice function if you remember that this is the geometric series. So maybe the best thing to do now is replacing the sum starts at n is equal to 1, so that starts at exponent 0. So I can just start n is equal to 0 and compute 10 times x to the power n. And this is a geometric series, and it's equal to 1 over 1 minus 10x, at least if x is small enough. And this is s times 1 minus 8x. So in the end, we get an equation for s, which is s, so the 9x squared is still here. S is equal to 9x squared times 1 over 1 minus 10x multiplied with 1 minus 8x. Whoa, that's S, that's our sequence. So now we go from a function back to a sum. Then we can read up our AN, the ones we are interested in. Let me get a bit of space here. So we want to find a sequence which a summation which rewrites that function gx. And now we really need a trick. That's a bit unfortunate, but essentially we do an ansatz. So we try to write 1 over 1 minus 10x times 1 minus 8x. We want to write it in the form a over 1 minus 10x plus b over 1 minus 8x. You can convince yourself that it is possible, but it's easier to convince yourself going backwards. So how would you add up these two fractions? Well, if you would add up these two fractions, let me get a preliminary color, which is not so important. Then what you would do is you would bring them to the same numerator. So you would take a times 1 minus 8x plus b times 1 minus 10x. And then you get the 1 minus 10x times 1 minus 8x in the denominator. So the denominators are right. And then you can see that you just have to solve this equation in order to get a constant. And now we're doing the other way around, and I remove that line again. So what are my A and B in this one? So what I wrote there, that this is equal to bringing them on the same side, a times 1 minus 8x plus b times 1 minus 10x divided by the same thing as on the left-hand side, 10x times 1 minus 8x. So these two things are the same, just by the rules of adding fractions. And we want to find a and b, and I find them slightly different than in the book. So I see this as an equation where I just have written, well, this should hold, but they have the same denominator. So I just have to compare the numerators. And what I want to get is a and b, and I have an equation. 1 is equal to a times 1 minus 8x plus b times 1 minus 10x. How to solve this? The first thing is we need two equations because we have two unknowns. But now we have actually here infinitely many equations. For every value of x, we get a new equation. And the trick is just to plug in two values of x. We take values which make our life easy. So the first thing is we plug in x is equal to 0, and then we get an equation. 1 is equal to a times 1 plus b times 1. Perfect. One equation says that a and b sum up to 1. We need a second equation, And I'm still struggling with that, but I can take breaks. So I found a nice value of x to plug in to get the next equation. Let's take x is equal to 1/10. So the value we plug in gives us 1 should be equal to a times 1 minus 8 divided by 10 plus, but I chose x to be smart such that if I plug it in, this entire second term becomes 0. And now I have something I can solve for a. A is equal to 1 divided by that thing 1 minus 8/10. And this gives us our value a is 5. And if a and b sum up to 1, then b has to be -4. Nice. So at this point, we can replace our a and b by 5 and -4. Getting a bit ahead with that exercise. So this is just the side calculation. And if you follow the script, then what was a and b? Let's put this in the corner that we don't forget it. A was 5 and b was -4. The last equation we had for s was s is equal to 9 times x squared. And then we have rewritten the term in the brackets as a over 1 minus 10x plus b over 1 minus 8x. So this was our equation, but now we know a and b, and we can plug it in, and we have a 5 and a -4. Oh, this is nice. Why is this nice? Because we can write whatever is written here as a sum. So so in the step before, we were writing a sum as 1 over 1 minus 10x, and now we can go backwards. So this is by, you can recognize the result of a geometric series here. And if you want to write this expression as sums, you get the following. You still have the 9x squared here. The 5 we take out, and then we get our sum over 10 times x to the power n, starting in n is equal to 0, I think, because it's a geometric series. We take the -4, and we get again the sum starting in n is 0 to infinity of 8 times x to the power n. And now let's pull the 9x, etc., inside again, and remember that s was equal still on the board. The sum of n is equal to 1 to infinity a n x to the n, and the right-hand side I'll write as a sum, and then it's 9 times 5, 45. And then it's 10 to the n. And there's x to the n plus 2, and the 2 comes because I have a factor x in front of here. And I can also rewrite this expression. So it will be plus 9 times 4 is 36 times 8 to the n times x n plus 2. And the sum is going from n is equal to 0 to infinity. That was our sum starting in 0. From this one, you can almost see the ANs already, but you have to do one additional transformation to write this as a sum from 1 to infinity. How do you do this? Well, you have to substitute the right value for you have to substitute. So essentially, this is the product starts with the power starts with the value 2. So if n is equal to 0, then it's x to the 2. So if I rewrite everything, then I'm starting in n is equal to 2. And then I can subtract that 2 here. I can subtract that 2 here. But I also have to subtract it here. And I have to subtract it here. Okay. So because a1 is equal to 0, so we can either write a sum over the n's starting in 2, or we can write a sum over the an starting in 1. So I've made it a 2 here, and then you see the nice correspondence here. Let me get a color to celebrate. Here you have an expression involving the ANs. And here you have an expression involving what the ANs are. So if I summarize it, it's AN is equal to 45 times 10 to the n minus 2 minus 36 times 8 to the n minus 2 minus 1 minus 2. And if you have gone so far, then what you really want to do is making a check if this formula at least works for the first 2 or 3 values. Otherwise, you can identify that you made a mistake. So I'm not doing this today. So you can check for yourself, because I am lucky that I know that this is right, because it's from the script. Okay, let's. Maybe this one is easy to check. Sorry for having one last thing. So if I take n is 2, then it's just 45 minus 36. And that gives me 9. And we know that A2 is 9 because that's how we started off with the day. So thank you for your attention. And that is enough for now.